Our next speaker is Boyce Griffith from the University of North Carolina at Chapel Hill, and he's going to be doing the more advanced part of the immersed boundary method in IBM.
So I think I mentioned this in the previous. Let's see if this works. Going to work. I might have to do it. One more time.
Look at the alpha. It's like
there it goes. Oh, right. So, oh, but now where did my?
do I have to reshare?
Someday I'll know how to use Zoom. Okay, so I kind of mentioned this during Aaron's tutorial, but I think more material than I can cover, and so I have kind of a possible outline of things, but so we've been working for a while on immersed boundary-like methods for handling volumetric structures with complicated constitutive models. And so that's potentially part one. There was some interest in how to build these regularized delta functions. And so I had that as possibly part two, although we could maybe start with that. We've made a little bit of progress on modeling material failure for rubber-like materials using a modeling framework called peridynamics, and so that could be part three. We have what is a new approach to fluid structure interaction that uses the immersed interface method, and then we've got some progress towards effective solvers for implicit immersed boundary formulations, which is definitely the least developed of the 5 possible parts, but good start. If anyone want to voice an opinion? All right, so let's start with elastic structures. So in IBAMR, these methods have a name that I picked that I don't like, called immersed boundary finite element, which doesn't really make a lot of sense because they're volumetric things. But so this is the IBFE module in IBAMR, but we've been trying to use a name that I think is more descriptive. It's the immersed finite element difference method. So this is the immersed boundary method with immersed elastic bodies. A lot of the notation Aaron conveniently introduced in part 1 of the tutorial, but so we're doing here we're doing large deformation continuum mechanics kinds of models of the immersed structures. So we've got say reference coordinates. So these could be the coordinates of the structural body at time 0, or it could be some kind of virtual reference configuration that you never actually achieve. It doesn't really matter, but you've got some kind of material coordinate system, kind of a physical coordinate system that you're mapping into current coordinates with this deformation map chi. And to understand what the model does, we need to talk a little bit about kind of what the stresses look like. What we have is sort of a standard immersed boundary kind of setup where we have fluid-like stresses throughout the entire computational domain. So there's fluid-like stresses in the fluid region. So this is supposed to be blue. Is it blue? I'm not sure. It's maybe violet. Like, yeah, I don't know. So I'm a little bit colorblind, but so this is the fluid region. When I was picking colors, I thought it was blue. And then this is the solid region. We've got fluid-like stresses everywhere. And for simplicity, the fluid-like stresses look like stresses of a viscous incompressible fluid, and described using the incompressible Stokes equations eventually. And then in the solid region, there also are solid-like stresses. And the solid-like stresses come from the constitutive model that's describing the elastic response of the structure. What I'm going to be showing is mostly going to be using hyperelastic material models. So there's some strain energy functional of the deformation gradient tensor. So the modeling work in terms of describing the structural response goes into describing the strain energy functional W. At the end of the day, we have a Lagrangian description of the stress. We like to formulate things using the so-called first Euler-Kirchhoff stress. So we're getting forces in the current configuration, but parameterized by coordinates in the reference configuration. But if you want to think about what the effective stress is for the fluid structure system in the solid region, you need to convert that into the corresponding Cauchy stress. And so this is the Cauchy stress that corresponds to this first Euler-Kirchhoff stress. But so this is kind of like some kind of large deformation version of like a Kelvin-Voigt material. So it's like you can think of it sort of in parallel. There's a viscous component and an elastic component. And if you don't like this way of modeling elastic structures, I have a story to tell you a little bit later about how to not have these fluid-like stresses show up in the solid. But for now, they're going to show up in the solid. So the equations that we wind up with look a lot like the immersed boundary equations that Aaron showed. So we've got the momentum equation. So this is the momentum equation of the coupled fluid structure system. So this is like kind of the key, I guess, philosophical approach of the immersed boundary method. We have one momentum equation that we're going to use for everything. In the fluid region, it's the fluid momentum. In the solid region, it's the solid momentum. These terms are where the fluid-like stresses are showing up, and they're distributed throughout the entire computational domain. And so in particular, there are these fluid-like stresses that are in the solid region. And then there are additional elastic forces that show up just in the solid region. And those elastic forces are defined in terms of the first Euler-Kirchhoff stress tensor, so the solid stress tensor, which is written in Lagrangian form. So in the interior of the solid, we've got the divergence of the solid stress. And so these are the resultant forces that are generated by the deformations of the structure kind of within the solid region. And then there's an additional force that looks like a traction force. So this is a force that's concentrated along the fluid structure interface. And one of the ways that you can kind of think about this is you could sort of think about a structure that's made of a bunch of springs, maybe. And in the interior of the region, you've got kind of balance of all the springs in the different directions. And then you're going to have some unbalanced spring forces that are along the boundary. And these sort of unbalanced spring forces are these traction forces that are just showing up along the fluid structure interface. So these are these interior forces are nice regular things. They, even though we're using the delta function to communicate forces from the Lagrangian frame to the Eulerian frame, this is not a singular force density. On the other hand, this is a singular force density that's supported just along this fluid structure interface. And so it does the same kinds of things that singular forces do in a regular immersed boundary kind of model. So it gives rise to stress jumps. And if you have thought about kind of stresses in solid mechanics models, you might worry about there being stress jumps. So it turns out that you need to have this boundary term along the fluid structure interface to give a jump in the viscous stress that counterbalances the jump in the solid stress as you go from the inside to the outside to maintain overall traction continuity. So the formulation here is set up in a way to ensure that you have traction continuity at the fluid structure interface. You've got force balance there. The equations in that strong form are a little bit difficult to discretize if you want to use some kind of complex geometry for the solid. And so in practice, we use sort of a partial weak formulation here. So we're going to replace these two forces, this interior force that's like the divergence of the solid stress, and this traction force that's just the solid traction on the interface, with one equivalent Lagrangian force density. And so you hit it with the test function, you integrate by parts, moving the divergence off of the solid stress and onto this test function, and you get this sort of weak statement of the combination of the interior force and this traction force. And so this thing now actually is singular. We're going to regularize it at the end of the day using a finite element method in a way that doesn't further degrade the order of accuracy beyond the order of accuracy that you get by using an immersed boundary method in the first place. And I guess I've neglected to mention it, but the solid moves in the same way that the boundary moves in an immersed boundary method. So we're going to take the Eulerian velocity and integrate it against the delta function to get the velocity of every material point within the solid. So those are the kind of the basic equations here. Questions? Does this sort of make sense? So let's keep going. So one of the questions you can ask is, does this work? So we're going to use so this is like think about it's like a rubber band. You're going to twist it up, and it's a volumetric model. Aaron kind of alluded to this in the first part, but the solid body is immersed in this kind of incompressible model. So the velocity field that determines the motion of both the fluid and the structure is incompressible. So it's divergence free. And so in particular, the motion of the solid should be incompressible as well. Okay, so we're going to take this. This is a so-called Mooney-Rivlin material. It's defined in terms of the first and second invariants of the of C. C is the right Cauchy-Green strain tensor, so it's F transpose F. So this is a kind of a pretty classical hyperelastic material model. And I'm showing you the motion of this kind of rubber band thing as we twist it up. And the colors are the Jacobian determinant. Jacobian determinant should stay 1 because the material is incompressible. And you can see that this does a really bad job. So it does a really bad job. And one of the things that's happening here is that we are really relying too much on the fact that the velocity field that we're using to determine the motion of the structure is an incompressible velocity field. And so I would say that there was a lot of, maybe a lot is an exaggeration. There's been work over the years that says, oh, if you use the immersed boundary method for these kinds of problems, you get very bad volume conservation. Period. End of the story. And it's the case if you don't treat the mechanics model sort of carefully. So this is a mechanics setup that is great if you ensure that the Lagrangian velocity field is exactly divergence free. So if you have an exactly incompressible solid mechanics formulation, then this is what you would want to use for your energy, and you would use this setup to compute your stresses and so on and so forth. But there are at least 2 sources of volume lack of volume conservation. So volume can increase, it could decrease. One of the sources of the lack of volume conservation for the numerical method is just this transfer operator that takes velocities on this background grid and puts them onto the structure. That operation, even if the background grid velocity field is discretely divergence free, isn't guaranteed to maintain that property on the Lagrangian structural mesh, unless you set it up correctly, and I'll show you that in a minute. But But so there's no guarantee that the velocity field that you get on the structure is incompressible. Even if the velocity field is incompressible, time stepping errors will also, in general, result in changes in volume. And so there's not really any reason to expect, unless you do something special in the way that you set up the coupling operators, that the velocity that the solid moves according to is going to, in fact, be incompressible velocity field. So what we did to try to fix this is sort of the simplest thing that you could possibly do. We added to the energy a term that blows up when the Jacobian deviates from 1. So we just add a volumetric energy. And so there's an extra parameter here that plays a role that's similar to the bulk modulus. It's not a true bulk modulus. The continuum model here is an exactly incompressible material. And so the bulk modulus, the true bulk modulus of the material is infinite. So this is what we've called a numerical bulk modulus. And so if you do that, then you get much more reasonable deformations. You still do get some volume change, more than we would like. And so the next thing that you can try to do is you can use what's called a modified deformation gradient tensor. So here, what we are using is a deformation gradient tensor f bar, which is j to the minus 1 over d times the original deformation gradient. And so this is a deformation gradient tensor, a modified deformation gradient tensor that's set up to only encode the deviatoric motions and not the dilational motions. And this is a very standard approach in computational mechanics for dealing with nearly incompressible materials. And if you do that, lo and behold, the thing works. So if you look at, for instance, we're looking at the tip displacement of this rubber beam as we twist it, and we're comparing to the tip displacement that we get with sort of a benchmark, exactly incompressible, large deformation, nonlinear finite element mechanics code. You can see that by setting everything up in the right way, you get results that, as you refine your grid, are essentially indistinguishable from state-of-the-art kind of low-order incompressible finite element mechanics model. So the method works. But you have to be careful about the way that you're formulating the energy that's describing the material response to get good results. Does that seem like it makes sense? All right. Questions? So I want to say a little bit about how the coupling scheme actually works for this. And so we want to try to leverage some of the finite element machinery that's available to couple the fluid and the structure, and to do so in an efficient way. So I didn't say it, but it was on the slide. So omega naught is the structure's initial configuration. Omega t is the structure's current configuration. Chi is the mapping from reference coordinates to current coordinates. And this is how we are defining the structural force that is driving the motion. So we're going to discretize this using standard Galerkin finite element methods. So we're going to have shape functions, so Lagrange basis functions that live on our mesh, and we're going to use those Lagrange basis functions to describe the structural motion. And so we're going to describe the overall motion of the volumetric structure by interpolating the displacements of the nodes. So here you can think of K as an index that's looping over all of the nodes. Phi K is a finite element basis function that's concentrated at node K. And so this is interpolating all of those nodal positions. The individual nodal positions are going to be functions of time. The basis functions are functions of space. And then you put them together and you get kind of this global field that defines the overall deformation. And then we're going to do the same thing for the velocity of the structure and for the Lagrangian forces that are generated by the solid mechanics model. And so if you take these expressions and you plug them just directly into this Weeks form, and you rearrange things a little bit, what you wind up with on the left-hand side, going from here to here, is you wind up with these integrals of products of the individual basis functions. And so this is the well-known mass matrix that that if you've kind of done finite element stuff, you most surely run into. And on the right-hand side, what you have are integrals of the stresses, which you're going to evaluate in terms of the derivatives, spatial derivatives of the deformation, times the derivatives of the shape functions, of the basis function. And so this is commonly called a load vector. And so to evaluate the Lagrangian forces, you need to solve a mass matrix system where on the right-hand side, you're computing stresses multiplied times gradients of shape functions. Okay. So you can solve that, and you get forces that are at the nodes. And so I want to make sure it's clear. So we're solving for the nodal forces, but you are going to be able to evaluate those nodal forces. You can evaluate those nodal forces anywhere in the solid region because you have these interpolatory basis functions. So one of the things that we started doing when we first put this together is like, oh, let's just interpolate the forces to arbitrary positions within elements. Because at the end of the day, we want to take this Lagrangian description of the elastic force density and turn it into an Eulerian description of the elastic force density. And to do that, we need to compute these integrals of Lagrangian forces times regularized delta functions. And so how do you compute integrals in finite element methods? Has anyone computed integrals for finite element methods? What's our favorite tool for doing this? Gauss quadrature. So just throw on Gauss quadrature nodes. And so you've got, say, Gauss quadrature nodes, and you can interpolate your forces to those Gauss points, and you get weights for each of the Gauss points, and you can then take those weights and you can use them to sum up the contributions of the forces times the regularized delta functions. And that's a reasonable thing to do. You could also, instead of using a Gaussian rule, you could maybe just use a nodal rule. So you could just sample, to evaluate this integral, you could just sample the forces that you've already computed at the nodes, and you can just directly spread those forces from the nodes of the mesh to the background grid. That's a reasonable thing to do as well. So there's a little bit of a trick that you have to play in order to get this to work well. So the nodal quadrature rule, I want to try to make sure this is clear. So the nodal quadrature rule gives you quadrature weights. So the quadrature weights, if you think about it kind of element by element, this is going to be about a quarter of the area is associated with that node, about a quarter of the area of this element is associated with that node, and so on and so forth. So you get quadrature weights, and you can use those quadrature weights to define what's called a diagonal mass matrix. And so then you can go back and you can say, okay, well, with this diagonal mass matrix, I'm going to use this diagonal mass matrix to evaluate the forces. So what that says is that the forces at a particular node is determined by these integrals of stresses times gradients of shape functions divided by this diagonal mass, or this diagonal weight. This is just a different discretization. If I back up, this is just a different discretization of these integrals. So we need to compute these integrals somehow or another. What you commonly do to get what's called a consistent mass matrix is you just exactly integrate them. You can pick a Gauss rule that's a high enough order rule that you can that there's no quadrature error. But that gives you a mass matrix that has off-diagonal terms. You can also just say, well, I'm going to use the trapezoidal rule. I'm just going to sample everything at the nodes. And that gives you a different mass matrix. It's just a different numerical integration rule. And you can use that to, again, define forces from the stress integral. So with standard finite element mechanics methods, if you're using quadrilateral elements or hexahedral elements, if you're using these Q families of elements, you can use diagonal mass matrices to very high order and everything is fine. If you're doing things on simplices, so on triangles or on tetrahedra, diagonal mass matrices work great for linear elements, and they don't work at all for quadratic elements because the basis functions on the midpoints integrate to 0. And so that causes problems. So if you're trying to do this with standard finite element mechanics approaches, you have to be careful once you get away from lowest order finite elements. And it turns out that this is not a problem for this immersed finite element difference method. So in the immersed finite element difference formulation, force that we ultimately care about is the force on the grid. The force on the grid we get by summing up the samples of the forces on the mesh. So this is just the force at each of the nodes times the regularized delta functions times the quadrature weight. Now this guy here, this nodal force, is determined in the diagonal setup as just 1 over the quadrature weight times the stress interval. And so this quadrature weight shows up on the denominator, and the numerator. They cancel each other out. So the force on the grid is a sum of these stress integrals times the regularized delta functions. The weight just totally drops out. Totally drops out. So how does velocity interpolation work? For velocity interpolation, we do the same thing, but in reverse. So you can think of defining a velocity field, UIB, as the sum of velocities on the grid times regularized delta functions. In general, this velocity field, which is a nice continuous velocity field because our regularized delta functions are continuous, is not something that you can exactly represent using the finite element basis functions. And so if you approach this like you're trying to build a finite element method, what you might think to do is to take this velocity field that you want to use to determine the motion of the structure and to project it onto the basis functions. And indeed, that's what we do. Now, at the end of the day, what that means is you need to compute integrals of this immersed boundary velocity field times the basis functions. And you need to use a quadrature rule for that. If we use the same nodal quadrature rule that we used to define the mass matrix, because the basis functions are interpolatory, all that says is that the velocity of the nodes is what we get by sampling this IB velocity field at the nodes. And this is just back to what you would do in a regular old immersed boundary method. And so the way that this sort of all comes together, you want to use the same quadrature rule to discretize force spreading, velocity interpolation, and also the weak form of the divergence of the stress. And by doing that, you get a method that actually doesn't depend on the quadrature weights at all, which is kind of surprising. But a convenient thing about this is that we're able to use higher order finite element formulations without having to solve these sort of denser consistent mass matrix systems. So you get this efficient nodal coupling scheme. And so I'm now just going to show pictures of things people have done with versions of these methods. So these are jellyfish simulations that Alex ran. I think for this 2017 paper, I think.
2021. That was 2021.
Oh, all right. Well, anyway, it's for something that's on the slide somewhere. So this is a jellyfish bell that is using a mechanics formulation that is implemented using a version of this IFED method. And I guess I should have asked you what you're doing in your lightning talk. Maybe I'm showing things you're already going to be showing.
Not jellyfish.
Not jellyfish. Okay, great. So, so Alex and Laura Miller used these kinds of models to perform different kinds of computational experiments with these sort of jellyfish bell models. I really like this one. This is my favorite one. What they're doing, they're looking at the impact of having a muscle activation wave speed. So the color is showing the muscle activation sort of parameter that's a function of both space and time here. And so if you have very slow activation from right to left, the jellyfish basically swims up. It swims up very slowly, but swims up. If the activation speed is a little bit higher, then the jellyfish bell will start to turn. And then I think it's easy to convince yourself that if you make it really fast, it's as if it's activating synchronously and it swims back up again. So there's this non-monotonic relationship between activation speed and the overall kinematics of the model. I like this movie, although for some reason it started strobing for me. Does this movie strobe for you, Alex?
Yeah, it's a visit issue.
It's a visit issue. But so Alex has also been using these kinds of models to look at the fluid dynamics of oh, where did it go? Of how do you say it?
Tomopterids.
Tomopterus, which lives deep in the ocean. So Laura has been using these things to look at insect flight. This is a movie that's, I think, a few years old now, where they were looking at the bristled wings of these parasitoid wasps. So these are really tiny insects that fly at Reynolds numbers of like 20 or something like that. And so the overall aerodynamics here are very different than what you see in insects that are flying at a kind of higher Reynolds number. We've been building all this stuff so that we can model blood flow in the heart. And so I can't resist the opportunity to show you all our heart model. So this is a model of the heart that is built from computed tomography imaging of a healthy subject. It has all of the structural features of the heart. So heart has 4 chambers. The upper chambers are the atria, the lower chambers are the ventricles. The right side of the heart receives deoxygenated blood from the body, pumps it into the lungs, where it's reoxygenated, returns to the left atrium. Left atrium is like a primer pump to get the blood into the left ventricle, and then the left ventricle is responsible for distributing the blood throughout the body. The images look something like this. These are not the actual images that we use. These are from this nice website called radiologyassistant.nl that has lots of great annotated CT images of the heart and other organs. Ultimately, you have to somehow extract the anatomical information from those kinds of grayscale images. We then make volumetric finite element meshes. In the simulations that we have been running so far, we have volumetric descriptions of everything, including these thin cables that are modeling what are called the chordae tendineae, which are these sort of cords that attach to the papillary muscles and to the leaflets of the mitral valve and the tricuspid valve, the inflow valves. We have to model the fiber architecture of the heart somehow or another. And the approach that we use is something called harmonic interpolation, where you sort of map out how the depth of the tissue as you go across the wall, so that you can capture transmural fiber rotation. You get these kinds of nice harmonic fields that you can use to build up fiber models. This is a visualization of the fiber structure for this thing. We similarly have, again, kind of a continuum description of the fiber structure for the valve leaflets. The heart valve leaflets are extremely anisotropic. With these kinds of mechanics models, you can capture the mechanical properties. In this case, this is looking at the passive mechanical properties of ventricular myocardium, ventricular muscle. And there are these 6 different simple shear directions. And you can see, if you look at sort of stress strain data, that you get different stress responses for the different kind of characteristic shear directions, and you similarly get highly anisotropic material responses for the valve leaflet. So this is looking at the stress response in the fiber direction and in the cross fiber direction. The whole thing is so the heart is not an island. The heart is surrounded by the pericardium. We don't want to model the pericardium. Pericardium is like a sac that the heart is inside, and so we instead use a reduced order model of the pericardium where it acts kind of like springs and dashpots. And similarly, we don't model the whole circulation. We are using sort of reduced order models of the systemic and pulmonary circulations. And so you put everything together, you get stuff like this. So this is the heart model where what we're doing here is we are prescribing activation timings for the upper chambers of the heart. So that's this blue curve here. We're prescribing activation timings for the lower chambers of the heart. This is a red curve here. The atria contract synchronously, spatially synchronously. The ventricles likewise synchronously contract sort of spatially homogeneously. And then it does what it does. So we're not prescribing any of the motion here. What we get is a model that, I'm going to skip over a little bit, that automatically captures what are called pressure volume loops. This is the pressure volume loop in the left ventricle of the heart. So this is looking at the pressure in this chamber as a function of the left ventricular volume. And what you get are all four phases of the cardiac cycle. So you have diastolic filling. So this is when the ventricle is relaxed and is filling up with blood. Then when the ventricle starts to contract, you get this period of what's called isovolumetric contraction. And so that's when both the inflow valve, the mitral valve, and the outflow valve, the aortic valve, are closed. Eventually, enough pressure builds up in the ventricle to open up the outflow valve, the aortic valve. You get systolic ejection through the aortic valve. The ventricle eventually relaxes. And when the ventricle relaxes, the pressure drops. When it drops enough, the aortic valve will close. You get this period of isovolumetric relaxation. When the pressure in the ventricle drops below the pressure in the atrium, the mitral valve opens up and you get diastolic filling again. So you get this cardiac cycle. Let's see, is my thing going to work? I think I'm going to skip this, but we get very realistic looking flow traces out of it. An interesting thing about the model is that it automatically captures what's called the Frank-Starling mechanism. So this Frank-Starling mechanism says that when you have more filling, you get more ejection. And it sort of automatically captures that by virtue of the way that the mechanics model is set up here. And I'm going to skip over this. One thing I'll say is that it's very easy to change the way that the mechanics models are implemented because we're doing things for now in an explicit way. So you just need to have a function that evaluates your stress from the deformation gradient tensor. And these things are not so complicated. And so you can play around with different stress models. And so this is looking at two different models of active contraction. One is a model where there's contraction along the muscle fibers and then a corresponding isotropic expansion across the muscle fibers, which is what you might think of as the way that muscle works. This is a model where you have contraction along fibers and contraction across fibers in one direction and not in the other direction. And I can explain later why this makes sense. This orthotropic contraction model gives you much more realistic apex to base shortening and wall thickening as compared to this transversely isotropic model. All right, so we've got a framework that lets us use immersed boundary type methods to do pretty complicated sorts of constituent models for hyperelastic, nonlinear material models. You know, there's not really any restriction to hyperelasticity. Sort of anything you can describe with a stress tensor and some state variables you can in principle use. But to get this to work well, you do have to be careful about the way that you treat the material model. And so in particular, you can't assume that the incompressibility that shows up in the continuous equations carries through to the discrete formulation. So what we do in our sort of production runs is to adopt this nearly incompressible elasticity formulation. There are other things that you could do. But this is what we've been doing that seems to be pretty effective. To make these methods fast, it's worth going to the trouble to figure out how to make all the coupling nodal so that you only are coupling from the finite element structure nodes to the background grid and back. We originally were doing this with coupling that was using kind of Gauss rules, and computations were, I think, maybe 10 times slower, which was not something that we could afford to do for these large scale models. Okay. Questions?
For the for those fibers in the heart, as well as the those hairy wasp wings with all the, it looked like there were many hairs attached. Are those like meshed cylinders or?
Yeah. So these are meshed. These are for sure meshed. These are not. So what we have is just a material field that lives on the structure mesh that is the local. You can think of as it's setting up like a local coordinate system that is just another field that lives on your structure.
Well, initially they were like the fibers like going like through the chambers or something, not on the surface, but
yeah.
first ones you mentioned.
So these are these guys. So those are explicitly meshed. Those are what are called the chordae tendineae, the tendinous cords. Yeah. So everything here is volumetric mesh for everything.
So like ultra dumb question, can you do something with IBM or whatever that similar to regular Stokes, where you just have a 1D curve?
Yeah, you can now. It's something that wasn't easy to do when we first were putting this together, and in fact, we're in the process of ripping these out and replacing them with I think actually we're just going to have 2-point forces and see if that's good enough. Yeah.
Wait. So maybe in many generations previously, Peskin had this fiber structure of the heart wall using geodesics, something or other.
Yep.
This harmonic.
So
that you've done, how good of an approximation were those geodesics? Like, is that something that just will not work?
I mean, what I would say is that you could map any fiber structure onto this as you want. So there have been various groups that have looked at the effect of different kinds of descriptions of transmural fiber variation and things like that in cardiac mechanics. It makes a difference, but yeah. So the models that Peskin and McQueen put together use the fibers as the structure. And so that we're not doing that here. So we have a structure, and then on top of that structure, we have a description of the fiber directions. You can put any fiber directions on this as you like. So if you can compute geodesics, you can use those.
So it would make a difference, but not a big.
I would be surprised if it made a big difference. But yeah, you can map anything onto it that you can compute. And there are the way that we're building these things. There are ways to approximate geodesic surfaces, if that's something that you care about.
No.
I guess going back to like my somewhat niche question.
Yes.
If we're thinking about sort of the element quadrature.
Yes.
Rules, are those done every time step, or is it?
Yeah. So right. So Alex is asking about this picture here. So this picture, this schematic, let me see if I can walk through it again. So the finite element mechanics model tells us what the nodal forces are, And then because we are describing the solid structural force as a field that is determined by interpolating these nodal forces throughout the solid body, we can evaluate the forces kind of anywhere. And so in particular, you could evaluate them at Gauss rules that you're using to discretize these kinds of integrals. And so when we first put this together, the idea was, oh, I can put the nodes really far apart and not have leaks through the structure just by filling in enough quadrature points in the interior. And then as the thing deforms, you can change your quadrature rule so you have more points or fewer points to make sure that you have a particular kind of point density to avoid leaks. And it turns out that works okay if you don't have big pressure loads, but it doesn't work very well if you do have big pressure loads. And so a lot of it just depends on what you're trying to model. But if the mechanics are such that you have a big pressure difference as you go from the inside to the outside of the structure, you need to put these nodes close together anyway. And so as soon as you have to put the nodes close together, you might as well just use a nodal scheme. Does that make sense? But if you don't have if you have a model that doesn't have a big pressure jump across it, this elemental scheme can be faster because there can be many fewer structural degrees of freedom. We don't do it anymore.
Can I follow up and just ask about the implementation of this method in IBAMR and like the flexibility and the flexibility?
Flexibility in what respect?
Like,
so there's a flag that tells you what quadrature rules you use. A flag that says like to use diagonal mass matrices or not. And there are kind of runtime options that you can use to pick the interpolation order and things like that. So it's fairly flexible.
so like if someone wanted to build something, I don't know, something similar to one of the simulations
Yeah.
that you showed, like they wouldn't actually have to code.
No.
No.
Most of the work in making these models is making the mesh. If you've got anisotropic material properties, most of the work is coming up with some way to describe the kind of the local coordinate systems that determine the anisotropic material response. And then deciding kind of how you want to model the material in the first place. But most material models, the implementation is a handful of lines of code that looks like just kind of tensor calculus kind of computation. So nothing too onerous.
You do have to think about grid discretization more, though.
So what you want, so there's a lot of work that goes into coming up with good meshes. So you want to have a mesh that's pretty uniform. And some mesh generators are easier to get to generate more, relatively uniform meshes than others. Okay, all right. So that's part one. Oh, I might be going the wrong way. So I'm going to do. Let's jump to part two. Jump to part two. Oh, why does it do that? So let me tell you about delta functions. All right. So how do you build delta functions? So inverse boundary equations. These are the same equations basically that Aaron showed in part one. We have this singular delta function. Here, even though I've drawn it as kind of a thick thing, think about like the boundary case. So you've got a singular force that's distributed along this interface. And, so you can't directly implement a delta function on a grid. So what do? So in the inverse boundary method, the solution is to replace the singular delta function with the regularized delta function. And usually what people do is they use the same basic kernel function so that you think of the delta function as being a tensor product of one-dimensional delta functions. And usually people use the same one-dimensional delta functions for x and for y. And I'm going to explain a little try to explain why you might not want to do that. And then commonly, although not always, so Tom mentioned this as a thing that you can do to get improved accuracy for the methodology that he was describing this morning. So in immersed boundary methods, usually you tie in this regularization with the background grid. And for this all to work, it has to be the case that these things integrate to one. But beyond that, there's a lot of flexibility. So we're going to have these regularized delta functions in place of the singular delta functions. So common choices that have been used include kernel functions that were popularized by Charlie Peskin's Act in Numerica paper in the early 2000s, where he postulated a set of moment conditions along with a condition called the even-odd condition that give rise to a family of delta functions. So John Stocky's done some work in this stuff long ago. But this is the so-called 4-point delta function. So 4-point delta function satisfies two discrete moment conditions that guarantee discrete conservation of force and torque. Something called the even-odd condition that's designed to try to that was originally designed to try to mitigate instabilities that show up in so-called collocated discretizations of the Navier-Stokes equations, and then a condition that is commonly referred to as the sum of squares condition. That's sort of an approximate grid invariance property. You get this kind of bell-shaped curve. You could throw away the even-odd condition if you don't need it, and you get a 3-point function. But all of these functions wind up having expressions that involve square roots because of the sum of squares condition. So the sum of squares condition says that the sum of the squares of the weights, we want it to be a constant independent of where the regularized delta function is concentrated on the grid. And then this is sort of a combination of the first and the second moment conditions. This is the even-odd condition. So if we sum over even grid points and over odd grid points, we want to get 1/2. And so together, those ensure that the function satisfies the sort of 0th order moment condition. We've been using delta functions that are based on cardinal B-splines for a while. And so cardinal B-splines, if you haven't seen the construction, have this really nice recursive definition. You start out with this function called the window function. So it's just 1 at the origin. And when you get beyond 1/2 in either direction, it's 0. So the window function. And then you can define the n plus first cardinal B-spline as the convolution of the nth cardinal B-spline and this window function. So this is the window function. This is where you start. If you convolve the window function with itself, you get the well-known hat function, piecewise linear. Every time you do this, you get one higher polynomial order. So the 3-point B-spline kernel, you convolve the 2-point kernel with the 1-point kernel. And so this is a piecewise quadratic function with the support of 3 mesh widths. And then you can keep going. This is a 4-point kernel. It's piecewise cubic, supported over 4 mesh points. And if you iterate this, it ultimately will converge to a Gaussian, which seems like a nice property. Okay, so volume conservation. So this is the sort of, maybe this is, well, so this is a tutorial. So this is a computation that you can do. So if you think about a closed surface, it's going to move according to the fluid velocity. Sorry for changing notation here. We're going to use big X to denote the positions of the points on the surface that are going to move according to this velocity field. If we assume that the velocity field is incompressible, then you can compute the time rate of change of the volume of the region that's enclosed by the surface. And so the Reynolds transport theorem tells us that, well, so you move this guy under the integral, derivative of 1 is going to be 0, but then you have the surface term from the boundary moving through space. And then you can use the divergence theorem to convert this the surface integral back into a volume integral, and out pops the divergence of the velocity field, which is 0. And so the time rate of change of the volume enclosed should be 0. All right. So So let's do the simplest thing that you can do, which is example 0 in IBMR. We're going to have a one-dimensional closed elastic filament. So we're going to do this in 2D. We're going to put this in the periodic unit square. We're going to have a linear elastic force density. So this is exactly what you get if you discretize the boundary using linear springs with 0 rest lengths. So what should happen? Like nothing should happen. This is already in equilibrium. The velocity should be 0. If you start out with a circle, you should stay a circle. Forces should be oriented in the normal direction. The pressure should be piecewise constant with a discontinuity at the interface that's proportional to the stiffness of the boundary. And so then this is just a visualization. What happens if you use the 4-point IB kernel for this problem? This is looking at the area as a function of time. You get these spurious flows that show up along the boundary. So you get these kind of vertical flows that show up, and the thing just steadily loses area. It just steadily loses area. So the volume conservation is not good. It's not good. So there are two fundamental problems. Aaron already mentioned them, but I'll say them again. So and I already mentioned one of them. So one of the problems is that there's no guarantee that the interpolated velocity field is in any sense divergence free. So we have a way to analytically compute the divergence of this velocity field because the delta functions are continuous. We can talk about the divergence of this Lagrangian velocity field. There's no reason to expect that the Lagrangian divergence is going to be 0. There's another problem, and the person who I think identified this for the first time is Cole Gruninger, who's a just graduated PhD student at UNC. And the bigger problem with the immersed boundary method actually is that the spread force contaminates orthogonal subspaces. And so I'll explain what this means in a second. But forces that should look like gradients on the grid don't necessarily look like gradients on the grid. And if you have forces that give rise to flows that shouldn't exist, well, you get motion that shouldn't happen. So how can we fix this? Well, let's think a little bit about just how to talk about incompressible velocity fields in the first place. So I think a lot of us are familiar with the with a version of the Hodge decomposition, the Helmholtz-Hodge decomposition. For every velocity field, you can decompose it into a gradient component. So the gradient is some scalar function, and a rotational component that's the curl of some vector potential. And then in general, there's also this extra term, this harmonic component. Harmonic component a lot of times just winds up being 0 because of boundary conditions. And each pair of these subspaces is an orthogonal subspace with respect to the L2 inner product. So we can decompose a velocity field as a gradient plus a curl plus this harmonic component. You can recover the scalar potential and the vector potential by solving a couple of Poisson problems, or you can use projections, right? And so this is really where projection methods come from. So if you want to get rid of, if you want to get an incompressible velocity field, you can hit your vector field with this projection operator that's going to throw away the gradient part, or maybe you want to keep the gradient part and throw away the rest. So we could define the projection operator as I minus this thing. So it's the gradient of the inverse Laplacian of the divergence. The velocity field that shows up in the Navier-Stokes equations is an incompressible velocity field. And at least on a periodic domain, we can interchange the divergence and Laplacian. And so what that says is that the time rate of change of velocity is the projection of this part that comes from the convective term. plus this Laplacian term minus the projection of the force from the boundary onto the Eulerian frame. So as long as this thing is a gradient, and now what does it mean? It has to be a gradient in a distributional sense because it's a singular thing. But if it's a distributional gradient, then all that you're going to get at the end of the day is a pressure jump and no velocity. So when is this thing a distributional gradient? Well, it's going to be a distributional gradient, for instance, if you can write down the Lagrangian force as a force that's oriented in the normal direction for some constant times the magnitude of dx by d theta. And so this is going to be satisfied in a steady state case if the force is just related to the curvature and the normal vector along the interface. This forcing should produce no flow. And this is the forcing that shows up at the very beginning of my really simple test problem, right? And so something is being spread onto the grid that's producing flow that shouldn't produce any flow. So what's going on? So this thing, if we do it in a continuous sense, gives us a distributional gradient. But we're not guaranteed for it to be a discrete gradient if we don't construct the delta function in the right way. So it's not so hard to show that if you have this normally oriented unit force or constant force times this regularized delta function, this is in general not equal to some discrete gradient of a grid function. In general, it's not going to be that. And so if you don't have the force as being a discrete gradient, then you will get a flow. And that's the fundamental problem that we're running into. So how do you fix this? How do you fix this? So what you want to do is you want to have a delta function that gives us discrete gradients on the grid. So how do you do that? That seems like it might be hard to do, but it turns out that it's incredibly easy to do. So to make all this work, we're going to use a staggered grid discretization for the Navier-Stokes equation. So we're going to keep track of the u components of the velocity on the x grid faces. We're going to have the v components on the y grid faces. Pressures are the cell centers. This is my favorite way to solve the Navier-Stokes equations. It's got a very natural discrete divergence free condition. It satisfies something like a LBB condition. It's mimetic, so a lot of the basic fundamental vector calculus identities that you know and love all hold on this. And in particular, it has a discrete analog of this Helmholtz decomposition. So you can write down a velocity field on the grid as the sum of a gradient of a scalar plus the perpendicular gradient of something that looks like a vorticity. So it's the sum of a discrete gradient and a discrete curl. And further, these are actually in a discrete sense orthogonal to each other. So it really satisfies this Helmholtz decomposition. It's called the marker and cell MAC discretization. Why it's called that is a little bit of a story that I'm not going to tell right now. But again, the main thing is that we can always write any velocity field on this MAC grid as a sum of a gradient and a perpendicular gradient. And again, the main problem that we're running into is that standard constructions for the regularized delta functions mix the subspaces. They'll take forces on the boundary that should be converted into discrete gradients, and they turn them into things that have components that are both discrete gradients and discrete curls. So how do you fix this? We're going to use different kernel functions for different vector components. So we're gonna have different functions. We're gonna call them phi and psi. And we're gonna require that phi and psi are related to each other through this derivative property. So if you compute the true derivative of phi, you should get the difference of psi, which is maybe a funny property. Have we seen this already? Have we seen a version of this? We have, but we'll get to it in a minute. So, all right, and so then what do you do? Well, so now we're going to have this kind of funny regularized delta function that's that's sort of a tensor product still, but we're gonna write it in this vector form that I think will make sense when I show you how you do force spreading in a second. But so basically, what we're going to have is this function whose derivative is psi in the x direction and psi in the y direction for the x components of the force. And then we're going to swap it. So this bigger function is going to be in the y direction for the y component, and in the x direction for the y component. And so to go from forces on the boundary to forces on the grid, you can think of as computing the kind of element-wise Hadamard product of the boundary force and this funny anisotropic, what we're calling composite regularized delta function. So the x component gets hit with phi in the x direction and psi in the y direction, and the y component gets hit with psi in the x direction and phi in the y direction. It's not too hard to show that if you have a force that's just in the normal direction along the boundary, then the derivative property in the continuous divergence theorem. Now, I guess I haven't really made a big point about this. All of these properties, as far as I know, only hold if you have a continuous integral. Once you discretize the integral, there's some discretization here that shows up. You can show that this spreading of the boundary force gives you something that's actually a discrete gradient on the grid. What winds up showing up is you take the derivative of this guy in the x direction and you get that guy. And you take the derivative of this guy in the y direction and you get that guy. And that's really the key for showing that this happens. But again, the fundamental property that's important is that this force, when we spread it onto the grid using this composite regularized delta function, is a discrete gradient. It is a discrete gradient. And so it just gets absorbed into the pressure. It doesn't do anything to the velocity. Okay. And then you do the same thing in reverse to interpolate velocities. We're going to use this kind of Hadamard product to use a different delta function in some sense in the x and the y directions to go from velocities on the grid to velocities on the boundary. And because the functions are related to each other through this derivative property, you can show that the analytical derivative of this guy is 0. Yes?
How did you determine? How did you determine the psi?
So it came from here. So these kind of constructions have been known since at least the 80s to be a way of giving an analytic divergence-free reconstruction of grid functions. I found out about them from a paper by Schroeder and coworkers from 2022, where they were using this primarily as a way of reconstructing velocity fields. And I mean, the story here really is we started using these because we thought they would be good interpolators. And Cole figured out that they had this other property, which is they maintain these discrete gradient properties, which I think is actually a more important property than the divergence-free reconstruction property. So that's kind of how we did it. Okay, all right. So how do you build them? How do you build them? What do you actually use? Well, so use B-splines. Use B-splines. So the n plus first B-spline is the convolution of the n B-spline in this window function. So you take the derivative, and you get this derivative property. So there's this relationship between the continuous and the discrete derivatives of these B-spline functions that is exactly what you need in order to have this gradient preservation property. Okay, so what does it do? It gives you nearly perfect volume conservation, even when you discretize the boundary integral. This is a parametric resonance problem. I think Ricardo has worked on this. I think, John, you've worked on this. Other people have. So this is a problem at the very, very beginning of the computation, which was way in the past before the movie started. This was a circular interface. It's parametrically excited, so the stiffness is a function of time, and the thing will start to spontaneously oscillate. And so if you look at the change in area as a function of time, we can look at what happens as we increase the regularity of these composite B-spline regularized delta functions. And at some point, you get essentially machine precision accuracy from using these composite B-splines. If you use lower continuity order composite B-splines, you can get much worse volume conservation. And this is, I think, mostly related to time stepping errors. Like you're using you're using something like a Runge-Kutta method or something that's assuming that your right-hand side has some amount of smoothness to get a certain amount of accuracy that is just not provided if you've got these really low continuity order composite B-spline functions. But you can crank up the continuity order by just turning the B-spline construction crank, spitting out, higher continuity order cardinal B-splines, and eventually you get functions that give you essentially perfect volume conservation. We're also looking at a divergence-free immersed boundary method that was developed by Bill Bao when he was a PhD student working with Charlie Peskin, where they explicitly built the Hodge-Helmholtz decomposition as a way to construct analytically divergence-free velocity field to move the immersed boundary. That's whatever color that is. Is that gray? I'm not sure. I think it's that one. And then this is the 4-point delta function. So the 4-point delta function just kind of steadily loses volume. You can look and see what the impact of time stepping error is, and it's actually for these higher continuity order composite B-splines, it has very little impact. There's very little impact of time stepping. For lower continuity order composite B-splines, the impact of time stepping can be quite dramatic in terms of volume conservation. And then this is just the 4-point delta function. Okay, all right. So that's part 2 of 5.
Questions?
Questions? Yes.
Yeah.
But maybe before I stop, so it's really easy to do this on a mat grid. You just need to use different delta functions in the x and y directions for the x and y components of things. And this is another thing that I think Cole actually discovered, is you can do the opposite thing and you get a function that preserves curls. To preserve gradients, you want to use a bigger function in the direction that the force is oriented and a smaller delta function in the transverse direction. If you do the opposite, you can preserve curls exactly. And Cole's used this to build an improved version of thin wire model that's used for simulating radio antennas using Maxwell. Anyway.
Yeah, so I mean, I believe you that this works, but it seems a little counterintuitive because like earlier on, you were trying to preserve a normal component of something or other. I can't remember exactly. And so I would have thought you would want to apply your delta functions, like your B-spline, separate them normal and tangential components.
I mean,
you're doing this in X and Y.
It's doing just X and Y. X and Y, yeah, but it's because it's what shows up on the grid that matters. It's not exactly the orientation of the interface. It's what shows up as a discretely on the grid. Is it discretely a gradient or not?
Okay.
And that's just, is it X or Y? Not is it normal?
Yeah, no, I would have just, intuition sometimes wrong.
So the underlying grid matters?
Does the underlying grid matter? So I think that one of the really important things is you need to have, I think you need to have a background discretization that has some version of a discrete Hodge decomposition. I think that's pretty important. I don't know how, like if you wanted to use a co-located method where you have maybe velocities and pressures all at the same places on your grid, I don't know if you can do this. I don't know how to do it. For those kind of methods, I think, well, all right, I don't know how you do it with a compact kernel. If you can do it with a kernel that has infinite support, but I don't like to use those. Other questions? Let's see.
Owen.
So you mentioned that so all these identities hold when the integral is performed perfectly.
Yes.
And all the examples you showed were on a closed periodic loop.
Yes.
It's very easy to integrate pretty well on a closed periodic
Yes.
loop, right?
Yeah.
Like if you did this, for example, in IBAMR, where you have these much more complex structures, how does volume conservation go in that case?
What does volume conservation mean when it's open?
Okay, fair.
So away from the endpoints, it's going to do the same thing.
Yeah.
So I mean, it doesn't solve all problems. So like like this rubber band problem that didn't work well. These don't fix that exactly because the quadrature is not accurate enough at the corners, and so you have to be careful at these like this method doesn't fix everything. So if you have boundaries that have that are fundamentally less regular, then you need to develop probably the right kind of quadrature rules to account for those. And in particular, the nodal schemes that I like to use don't work very well. I mean, it's better than using isotropic kernels, but it doesn't have this kind of nearly perfect volume conservation. Yeah, I mean, so right. So when the rubber meets the road, for real problems, they don't work quite as well. But
an improvement over like.
But it's a big improvement, and it's a practically free improvement. You don't have to do anything. All right. We're at 5. Let me show you in my 4 minutes. Let me show you a little bit of
No, he shouldn't.
So we've been building for a while support for immersed interface methods in IBAMR. So the idea with this, if you have a singular force along a boundary, you can use that singular force to figure out stress jump conditions. So the lowest order ones, the normal component of the force gives you a jump in the pressure. The tangential component of the force gives you a jump in the shear stress. And you can build those into your discretization in a variety of ways. I like to use methods that are based on generalized Taylor expansions, where at the end of the day, you wind up, if you've got known discontinuities, you're just solving the regular old 5-point or 7-point Laplacian. You can use these to do prescribed motion. This is a problem that I think Thomas already left, but this is a problem we got from Fay and Rycroft, where you get nice, good results. But what I really want to get to is you can use this to do fluid structure interaction. I don't have enough time to tell you much about how the numerical method works, except to say that all of the coupling between the fluid and the structure happens just at the fluid structure interface and not throughout the body. And so that lets you put in whatever material model you want to have in the interior of the structure. And you no longer have unless you want one, you no longer have a viscous contribution to the structural response in the structure. So it's a little bit, too many slides. So let me just show you some movies. So this is a rigid body dynamics with this method. This is like I think this is fluttering. This is a fluttering plate. So this is, think of it basically like you're dropping a piece of paper and it's just kind of like gently fluttering as it falls down to the ground. We're comparing to some experimental data that were collected and without doing a huge amount of tuning, are able to quite accurately capture the dynamics. If you just change the angle of attack, you get tumbling. Did I ever say tumbling? Like anyway, it's one or the other. And again, so you get this kind of we capture these experimental trajectories. A really interesting thing about this approach is that it very naturally handles structures that are denser than the fluid, structures that are neutrally buoyant, and structures that are lighter than the fluid, without having what are called artificial added mass effect instabilities. So this is a buoyant sphere that's in a water column. It's a square duct, and so the square duct sets up, there's symmetry breaking. The thing winds up heaving back and forth once it reaches a critical Reynolds number and starts shedding vortices. So it does a good job of capturing that. You can make the material model whatever you want. So those were using rigid body dynamics, but you could just as well do elastic structural models. This is a kind of a silly. These are both kind of silly test problems that are good to show that everything works for. But we get these nice stable oscillations. I'm going to skip this. I'm going to skip this. And so then, so what doesn't it do well? So the thing that we're working on right now is to try to get it to properly handle contact, which is naturally handled by the inverse boundary method. I didn't really talk about that, but is not naturally handled here because you have to be much more careful about how the jump conditions interact with each other when interfaces get close together, and it's a real pain. It's not so much in applying the jump conditions, but in reading the velocities back out, which is painful. And so I have a PhD student that's working on this. We are not quite ready for prime time. So here, this is just something you can see without treating contact very carefully. This elastic body, it keeps overlapping with the nozzle that it's getting squeezed through. And so what we can do in order to avoid this without being very fancy is just add in a little contact model. So you get in a little contact model that only that gives you repulsive forces once the structure gets within less than a grid cell of another boundary. And so here in slow motion, we can look at it and we can see that indeed we can keep the thing from interpenetrating if we add in a contact model. So one of the selling points of the inverse boundary method is that you don't have to have a contact model to handle contact. It's a double-edged sword, right? So you don't have to put in a contact model, but if you don't like the contact model that it gives you, then there's not a lot you can do about it. So here, maybe you need to put in a contact model, but it means that, well, you can put in the contact model that is appropriate for the physics that you're trying to capture. We originally developed this with folks at the FDA who were interested in modeling these devices called inferior vena cava filters. They wanted to be able to compute stresses accurately, which is something that I don't really know how to do with inverse boundary methods, but we are able to do with these inverse interface methods. Right, so that's something that's in progress. A lot of it's in IBM now. It's very experimental. I would like it. It's more like a race car than it's very finicky. You can get it to work. It's expensive. But it's been fun to play around with. The big open problem for it really is that time step size restrictions are even worse for this coupling scheme than they are for the regular inverse boundary method, and it's becoming a real barrier for using this methodology for real problems. And so that's something that we're trying to figure out how to address. And I am out of time, but we've made some progress on efficient implicit solvers. Like, anybody's interested, I can tell you later. Thanks.